Hello, everybody. My name is Jason Etchingham. This is my presentation on molecular entropy, a study using 2-aminoethanol. Okay, molecular entropy measures the randomness or disorder within a system at the molecular level. It quantifies how energy is distributed among a molecule's different types of motion. So that's translational motion, which is the molecule's movement through space. Rotational motion, or it's spinning around its center of mass, and then vibrational motion, which involves the periodic vibrations of atoms within the molecule. Vibrational entropy is a specific part of the molecule's entropy that comes from these vibrations. Since these vibrations occur at fixed energy levels, vibrational entropy measures how the energy is spread out among them. This can significantly contribute to the total entropy of a molecule, specifically at higher temperatures. Okay, so a little bit of background. Vibrational motions are unique because they're quantized, which means that they occur at specific fixed energy levels. These energy levels depend on the molecule's structure and the strength of the bonds between its atoms, um, which determines how the atoms vibrate relative to each other. Every molecule has a certain number of vibrational modes. For nonlinear molecules, it's 3n minus 6, and for linear molecules, it's 3n minus 5, where the n is the total number of atoms in the molecule. So, for example, like a water molecule, H2O, has three vibrational modes, which is, 3 times 3 minus 6 is 3. Um, Yeah, so for this project, I focus on the vibrational entropy to better understand its role in chemical systems. I use a software called Gaussian, to calculate the vibrational frequencies of 2-aminoethanol, which is essential for determining how vibrational modes contribute to a molecule's overall entropy. Okay, so for methodology, I selected 2-aminoethanol as the focus of my calculations because it's pretty relevant in organic synthesis and has a manageable level of complexity. My workflow included several key steps. So first, I built the molecule in Avogadro. It's a software. Next, I optimized its molecular geometry in Gaussian and then performed frequency calculations. And I analyzed these results from Gaussian back in Avogadro. And then initially, I plan to calculate these vibrational entropies of a starting material and a transition state of this molecule that I've been working with in my organic chemistry research. But it turned out that that runtime on Gaussian was really long. It's a pretty complicated molecule, so I chose to just do 2-aminoethanol instead. Okay, this is the equation I used. Um, Basically, you got this equation here. The Kb is the Boltzmann constant. H is Planck's constant. You got T in Kelvin. Basically, what I'm solving for with Gaussian and Avogadro is this VI here, which is the frequency of vibrational mode. What I get is initially in centimeters to the -1. I convert that into hertz. But yeah, that's basically the purpose of this experiment and the idea, and this is the equation I used. So this is a little picture of the information I got, or the data I got from Gaussian, and then plugging it back into Avogadro. This is Avogadro right here with my molecule drawn out. And then this is the relevant data here on the left side. So see, it's the V, but it's in centimeters to the -1. So once I got that, then I was able to do this Excel sheet here where I plugged in all the values for V in that unit and then converted it to hertz, which was pretty straightforward. Just multiply it by the speed of light, basically. And then you get this. It's a bunch of different plugging in values and using Excel, very handy, and then doing the sum of all those values here to get this. So that was the answer I got for the vibrational entropy. That's in joules per Kelvin, and that's per molecule. So then I could multiply that by Avogadro's number here to get joules per mole Kelvin. So this is a little bit more of a scaled up answer and a little bit more easy to understand. Okay, so this is just kind of showing the difference in complexity of the molecules from my research that I kind of wanted to do initially. So with the transition state here versus what I ended up doing, you can really see the difference in complexity. So it's also like my first time using Gaussian, so potentially in the future, I'll be a little more used to it, and doing something like this would be a little easier for me. Okay, so for conclusion, the goal of this project was to calculate the vibrational entropy of 2-amino-ethanol as a way to better understand molecular thermodynamics. The calculated entropy was 6.19 times 10 to the negative 7, and that's joules per Kelvin, and that is per molecule. Then you can convert that into 37.3 joules per mole times Kelvin, and that's on a molar scale. This reflecting the molecule's moderate vibrational complexity. A major challenge I faced was the difficulty of working with a more complex organic compound and their transition states. It's required significant computational resources in Gaussian, which ultimately just took too much time. In the future, I plan to revisit these larger molecules and transition states and try it again. Hopefully, a little more experience with the system software will have better results on that. But definitely worked for the 2-amino ethanol, so I'm really happy with that. And some references, and I hope everybody enjoyed my presentation. Thank you.